네, 여러분, 안녕하세요. 네, 물리화학 수업을 시작해 보도록 하겠습니다. 지금까지 계속해서 엔탈피 관련해서 여러분 같이 배워보고 있었습니다. 그래서 여러분이 이제 기본적으로 엔탈피가 뭔지에 대해서 어느 정도는 이제 예측을 할 수 있을 것 같아요. 그러니까 엔탈피라는 거는 기본적으로 이제 프레셔스가 컨스턴트 할 때의 어떤 그러한 열의 출입들에 대해서 보통 얘기하는 거고, 이제 그 밖에 내부 에너지 같은 경우에는 이제 볼륨이 일정할 때의 그 열의 출입을 계산하는 데 조금 더 유리한, 쉬운, 간편한 그런 부분이 있죠. 그래서 그러한 부분들을 여기 했었고요. 그래서 그런 엔탈피의 어떤 그 확장표, 그러니까 화학 반응, 실제적으로 우리가 이제 화학공학이라는 학문에서 여러 가지 이제 화학 반응에 있어서 열의 출입이 어떻게 진행되는가 하는 거에 대해서 우리가 엔탈피 측면에서 얘기를 할 거고, 그러한 화학 반응에서의 그런 열의 출입을 얘기하는 어떠한 그런 학문을 열화학, 영어로는 thermal chemistry라고 부르고 있습니다. 그래서 오늘은 그 내용에 대해서 여러분하고 같이 이야기를 나눠보도록 하겠습니다. Okay, so hello everyone. So let's start this today classes. So far we have learned about this enthalpy, which can express about this energy transfer by heat in a system, especially for the constant pressure situation. So today we will enlarge the kind of concept for this thermal chemistry. And this thermal chemistry means the kind of study about this heat transfer, which are occurred during this chemical reaction. So that kind of thermal chemistry. So we will learn about this, how the kind of enthalpy concept can be used for this thermal chemistry. And then this, which kind of examples we can be seen in that kind of thermal chemistry situation. So let's see. First, what is the thermal chemistry again? The study of the energy transfer and heat during the course of chemical reaction is called as the thermal chemistry. Yeah, so maybe some of you guys will experience about the kind of experiments of some kind of a chemical reaction during your experimental lecture or some kind of the design classes. Anyway, during the kind of chemical reaction, there could be some kind of energy transfer, and that energy transfer usually has a form of heat. And the studying about that kind of energy transfer by this heat during this same chemical reaction is called about this thermal chemistry. So actually, this thermal chemistry is quite how can I say has the best area, but today we will only have some kind of a brief introduction of the thermal chemistry and some kind of basic concept for that thermal chemistry, because this is the kind of some introduction chapter. So we don't need to all understand about this best area of the thermal chemistry, but I just want to give you some kind of the fundamental terminology about the thermal chemist, and also some basic rules you can essentially use for your understanding of this chemical reaction. Okay, so now we have understand about this. What is the thermal chemistry, and let's see about the identification of Q. What is it? This is a heat. So the reaction occurs at this constant volume. is called as the internal energy, right? So if there is the constant volume, then the energy transferred by the heat will be same as this internal energy change, right? We learn these things. Right, yeah, right, sure, right? If there are constant volume, then the energy transferred by the heat to this system is equal to this internal energy change. So that's the thing. What I'm saying now. So, and the reaction occurs at this constant pressure is the equal to this enthalpy, right? So in terms of exothermic, so delta H will be negative. And in terms of endothermic, the delta H will be the positive. Because the exothermic is the, how can I say, produce heat, and this heat is transferred to the surroundings from this system, right? Because this is an exothermic process. So that's why this heat transfer in this system could be negative because it loses heat during this exothermic process. But this endothermic process, it will absorb some heat from the surrounding. Therefore, this delta H should be plus in this endothermic process. So what is it? This is the constant pressure. So this is the kind of one of the fundamental understanding for the thermochemistry. So first, this thermochemistry means the study about this energy transferred by heat during this chemical reaction. That is the thermochemistry. And the thermochemistry, so and consequently, I mean, finally, the thermochemistry is dealt with this, some kind of heat transfer through this system. So, but this, if there is the constant volume situation, then this kind of heat transfer, the amount of heat transfer in the system is equal to this internal energy change. And then the if the condition is that the constant pressure, then this the heat transfer to this system equal to this the enthalpy change. So that's so that is the basics of thermochemistry. Okay, so let's see. So now we will learn about this the standard enthalpy changes. So to understand the one of the basic concepts of this thermochemistry is the standard enthalpy changes, and then we will talk about the standard enthalpy changes. The point, so what is the key point? First, the standard enthalpy of transition is equal to this energy transferred as heat at this constant pressure in the transition. Actually, this is the same meaning of this sentence, right? So the meaning of the standard energy, so the standard enthalpy is the during the change of standard enthalpy during the transition is equal to this energy transferred as heat at the constant pressure in the transition. So this is the point A. like this the how can I say concept of this standard enthalpy change. And point B is the thermochemical equation is a chemical equation, and it associates changes in enthalpy. Right. So we will also talk about this kind of thermochemical reaction, thermochemical equation, and this kind of thermochemical equation is a chemical equation. So it's expressing about this how the kind of reactions occur in a chemical point of view. And then this is also expressed about this enthalpy change during this reaction. So you don't need to fully understand about this thing now because we will talk about these things in the next slide. So anyway, this is just to explain about this key point. So first thing is the standard enthalpy. This is the quite new concept for you. And the other thing is the thermochemical equation. And third thing is the Hess's law. And this Hess law states that the standard enthalpy of an overall reaction is the sum of the standard enthalpies of the individual reactions into which a reaction may be divided. So what this means? If there are kind of reaction, which is the A plus B equal C, then the standard enthalpy of this overall reaction is the sum of this enthalpy of A and B, right? So that kind of rule called as the Hess law. So through this class, through the chapter, we will learn about this standard enthalpy and thermochemical equation and Hess law. Okay, so let's start first. What is the standard enthalpy change? So delta H theta. So the meaning of this standard enthalpy is the change in enthalpy for a process in which the initial and final substance are in the same standard state. So now you have to understand this about standard states, right? So what is the standard state? The specification of the standard state. The standard state of a substance at a specified temperature is its pure form at 1 bar. Right? So the meaning of this standard state is the state of a substance at a specific temperature under this pure form at this 1 bar pressure. So that kind of situation is called as the standard state. So again, so now we know about what is the standard state. So the standard enthalpy change means the change in enthalpy for a process in which the initial and final substance are in their standard state. So if this kind of reaction is occur at this 1 bar and from its pure form, then that kind of a process called as the enthalpy change in that kind of process called as a standard enthalpy change. So the standard enthalpy change for a reaction or a physical process is the difference between the production in their standard state and the reactant in their standard state at all the same specified temperature. So what this mean? So the enthalpy change for a reaction. So for example, if this kind of the water molecule transit to this the vapor the hydrogen oxide. Then the this kind of a pure form at this 1 bar, if this kind of process occurs at this 1 bar, and then the difference between this product, this is a product, and this is a reactant in their standard state, called as this kind of standard enthalpy change. What this mean? So during this kind of process, there could be heat transfer, and this heat transfer should be equal to this the enthalpy change. And this kind of enthalpy change for this kind of reaction at this standard state of substance called as the standard enthalpy change. So for example, the delta vapor H, etc. This is the standard enthalpy change of this kind of reaction from this rich H2O to this gas H2. And this is occur at this kind of 373 Kelvin. And this enthalpy change will be 40.66 kilojoule per mole. So this kind of concept called as the standard enthalpy change. So maybe it could be a little bit complex for you because the concept of this kind of standard state might be new to you, but it's not that complex. I mean, this is just kind of simple enthalpy change. What this means. So if because this kind of the reactions occur or some kind of chemical reaction occur at this constant pressure, and this heat amount of heat transport to the system is equal to this the enthalpy change. This is what we learned. And we just simply enlarge this kind of system to this standard state. So because for there should be non-standard state, so that's why we just want to simplify the kind of chemical reaction to more or easier calculation of this kind of enthalpy change. So that's why we use this kind of standard state. And because this kind of concepts could be new to you, so that's why you will feel this process is complex, but it's not that. It's definitely fundamentally similar to this the general concept with enthalpy change. But anyway, so the standard state is basically occur at this the 1 bar. What this means? This is the constant pressure, and it has a pure form like this. So that kind of the change in enthalpy for process in which this initial and final substance are in their standard state, we call this the enthalpy changes, but standard. So we just put this kind of setup to differentiate this kind of concept for just general enthalpy change. So the standard enthalpy change, so how can you calculate this standard enthalpy change? It's a simple, we can just simply minus this H2O, the reactant. So we can just, the amount of this difference between this, the reactant and this product stage of enthalpy. So we can just simply minus these two things, then we have this kind of values, right? So let's see. So because this is the plus 40.66 kilojoule per mole, so that's why this kind of reaction is the endothermic process. What this means? So it absorbs this heat from this outside, then it becomes vapor. The H2O become vapor. And if that kind of things occur at this 1 bar, so what this means is the kind of real situation. So we call these things as the standard state. Okay, so now we basically understand about this standard enthalpy changes, and then now we will talk about this enthalpies of physical changes. So let's read this sentence first. So standard enthalpy of transition. So what does it mean? The standard enthalpy change that accompanies a change of a physical state called as the standard enthalpy of transition. So what does it mean? For example, yeah, let's see. There is some kind of water molecules, and it becomes this vapor. And the states, physical state of this molecule is the change from the liquid to this gas. What this means? There are the physical change, physical state change. Right? So this kind of a concept called as the standard enthalpy of transition. So how can I say? So there is the standard enthalpy change and this kind of relation. So standard enthalpy change is the one of these standard enthalpy change. I mean, the standard enthalpy of transition is the one of these standard enthalpy change. Okay, so for example, this is example. So standard enthalpy of a vaporization. What this means? This is the vapor H, etc. And standard enthalpy of fusion can be called as the so yeah, so this is the standard enthalpy of vaporization. So this is also standard enthalpy of transition. And standard enthalpy of fusion is the solid to liquid. So it occurs at this 0 degrees C. What this means? So 273 Kelvin. And this enthalpy is the 0.10 kilojoule per mole. So at the 0 degrees C, the solid water, the ice, absorb this kind of this amount of heat and change its physical state to this liquid. And the kind of enthalpy change called as the standard enthalpy of a fusion. So this is kind of how can I say? So the rules. There's some the scholar made to communicate about this kind of this thermochemistry. Okay, so now we know about what is the standard enthalpy change and enthalpies of physical changes too. So this is the tables for the standard enthalpies of fusion in vaporization at the transient temperature. So for example, for argon, the standard enthalpy of fusion for argon is the about 1.188 kilojoule per mole, but the temperature is the 83 Kelvin. And the vaporization for argon has the 0.6.5 kilojoule per mole at this the 87 Kelvin. So that's why at the room temperature, this argon is already gas stage because this is already far above of this vaporization temperature. So anyway, yeah, it spent this kind of heat to make the kind of a state transition. And this C3H6 is this kind of a temperature for fusion, and the enthalpy change of standard enthalpy of this fusion is the 10.89, and vaporization temperature for fusion is the 30.8, right? So actually, so this is the benzene. So that's why the, how can I say, some oil. So benzene is a type of oil. So this oil requires some kind of a temperature to be boiled. So usually it is smaller than the water, right? But this the temperature for this benzene is the higher than this the water. So that's why this kind of oil is not solidified at this 0 degree C. Okay, so this is the water. We have already know about these things. In terms of helium, has the fusion, the enthalpy, standard enthalpy of fusion is about 0.021. And for vaporization, it's 0.084. So you can see it's almost impossible to see this kind of liquid type or solid type of helium because the temperature should be extremely low to make this liquid type or the solid type. So that's why we can only see this gas types of the helium, and also how can I say, the enthalpy changes. Standard enthalpy of this fusion or vaporization is also much smaller than this kind of water or some benzene, even smaller than this argon. So the reaction of this helium is the much quicker than this the other types of chemicals. maybe hydrogen should be much smaller. Right? Yeah. So now we have learned about this enthalpy of physical changes. Okay, so there are different types of enthalpies of a transition, right? So now we learned about this is kind of the phase transition concept. So we call that some kind of phase alpha to this phase beta. So they can call as the enthalpy of a transition. And there is also enthalpy of fusions, which is the solid to change of a state from solid to liquid. We call that things a fusion. And what is the vaporization? So you know it. So if the states change from this liquid to gas, then we call that things as a vaporization. And sublimation is the state change from this solid to this gas, right? So we call this sublimation. So fusion is a solid to liquid and the vaporization to liquid to gas. But if a solid directly go to this gases, it's called as the sublimation. This kind of situation you can see in the dry ice system. So dry ice is the directly vaporized from the solid to the liquid, solid to gases. So that kind of things called as the sublimation. And in terms of mixing, if you mix two things in a one, so pure things in a one, then we call that is the mixing. And solution means there is some kind of solute, for example, some powder particle or some kind of things into some the metric system, then we call system of a solution, we call as the solution. The hydration is the change of a state from gas phases to this aqueous phases. I mean the liquid phases. We call this the hydration. And atomization is the how can I say, split some kind of space into the atom side. Then we call the kind of things as the atomization. And our ionization is the how can I say, reaction to produce the kind of ion plus electron, and that kind of a reaction called as the ionization. And electron gain is the how can I say, if some kind of molecule gain some electron and become this kind of ionization system, and we call that as the electron gain. And reaction, this is the what we frequently see through this chapter, is the there could be some reactant and it changed to this product. And combustion is there is some kind of compound, and this compound is the react with this oxygen. And then it produces some kind of carbon dioxide plus this H2O. And formation is the making some kind of element to this compound. They call this formation. And activation is the reactant from reactants to this activate complex. So there are a lot of different types of transition from the some A state to this the B state, and depending on the mechanism of the transition, we will have different types of transition the name, and then symbol for this kind of transition also have different name. Actually, it's just the extracting some of a few characters from each word. So for example, for transition, it has this delta TRSH, and for fusion, it's a delta FUSH, and vapor, sublimation, mixture, solution, hydration, atomization, ionization, electron gain, reaction, combustion, formation, and activation. Yeah, so because the usually people use this kind of a terminology to explain about their reaction, so that's why you have to at least know what this kind of a terminology means to have the how can I say some unlimited communication with some kind of engineers about this field. Okay, so let's see. Now we know about this the enthalpy of change. So let's see. So enthalpy. So I would like to say, let's see. So enthalpy is a state function. What this mean? So it doesn't consider about this kind of way how to get this final stage. They right. So they only see this initial stage and this final stage. So we can only consider about this about the kind of reaction, and then we can only consider about this initial stage and this final stage. So let's say, for example, if there is some kind of a sublimation process, so what is it? This is the solid H2O to this the gas H2. So the change of enthalpy, I mean the enthalpy of transition is the can be written as the delta SUB, delta sub H zeta, right? So this is the delta sub H zeta. And there could be this kind of reaction from this solid to liquid and the liquid to gas. And the amount of this delta sub and this sum of these two things should be same because this is the state function. So it doesn't consider about independent about this kind of the stage of way to get this final stage. So that's why it's there's a two way to become this gas phase of this H2O from this solid stage. First is the sublimation, and the other thing is the fusion plus vaporization. So fusion plus vaporization. So that's why in that case we can say this H2O solid to this liquid. This is the fusion enthalpy of fusion, and this liquid to gases is the enthalpy of standard enthalpy of vaporization. So that's why this overall from this solid to gas of H2 should be the enthalpy standard enthalpy of a fusion plus standard enthalpy of vaporization, and this will be same. Right? So the overall result of the indirect path is the same as that of the direct passes. So therefore, the overall enthalpy change is the same in each cases. So this is the what this means. So direct way and indirect way, we have same amount. So this is the same. And the standard enthalpy changes of forward process and its reverse differ in sign, right? So this is the this way and this way we have same amount of absolute value, but they have a different sign, right? If this is a plus and this will be minus, but the absolute value will be the same. This is because the enthalpy is a state function. Okay, so now we can also see this kind of lattice enthalpy. So lattice enthalpy means the change of standard molar enthalpy for some kind of reaction. So what this means? There is a, how can I say? It's the, 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 the kind of divided reaction of some kind of reaction. And there could be, you can simply, some of these things and some of these things should be same. So it's also same types of the enthalpy system. Right, so this Born-Haber cycle is the one of the examples. So a typical Born-Haber cycle for potassium chloride, it consists of this kind of steps. First, this sublimation of potassium solid to gases, and dissociation of chloride gases, and ionization of this process, the potassium gas state, and electron attachment of chloride from this here to here, like this. So finally, they have this kind of a system. And the formation of solid from these gases, I mean, what is the gases from the solid is the minus delta HL. And the composition of this KCl again to this here. So the sum of this enthalpy change is equal to zero. I mean, if this KCl to the how can I say of their chemical reaction during chemical reaction, we have this way and this way. We have the sum of this all this process should be equal to zero, right? Because this is the plus and this is the minus. So that's why we can simply delta HF equal as uh, the 717 kilojoule per mole, right? So this is all this kind of thing is because the enthalpy is the standard function. Okay, so let's see about this enthalpies of chemical changes. So during this chemical reaction, what kind of enthalpy change can be occurred? So we can see. So there is some thermochemical equation which can express about this kind of chemical change. So there is a two-way to explain about this kind of thermochemical equation. So first, I'm sorry. So the enthalpies of chemical change, I mean the meaning of enthalpy change during this chemical reaction. So there is a two-way to express about this kind of enthalpies of chemical change. First, we can draw like this kind of a thermochemical equation. This is a combination of a chemical equation and the corresponding change in the standard enthalpy. For example, if there is this kind of a reaction, it's the methane to the oxygen and carbon dioxide and this 2H2O molecules. And this is the chemical equation. And then if we write this the standard enthalpy change of this reaction, and this is called as the thermochemical equation. So delta H etc. is the change in the enthalpy when this reactant in their standard state change to this product in their standard state, right? So the sum of this enthalpy change from this here to here, so difference will be written as the delta H etc. So this is the kind of pure separate reactant in their standard state, change to this pure separate product in their standard state. What this means, there's the two separate reactants, and then change to this two different standard state of product. Right. So this is the kind of the also the meaning of this standard state. So this is the one way to express about this kind of enthalpies of chemical changing. The first one. And the other one is we can simply write this standard reaction enthalpy. So here we just write this only, how can I say this, just the kind of a standard enthalpy change, but here we write this standard enthalpy of a reaction. Right? The difference of this is the, how can I say, this is kind of more specified concept for this reaction. So almost a similar concept actually. So for reaction of the form 2A plus B, from 2A plus B to 3C plus D, this kind of reaction, then the standard reaction enthalpy can be changed, can be calculated by this like this, the product enthalpy change minus this reactant enthalpy. So difference is they are the molar enthalpy. So that's why they have some kind of this unit per mole. So the HM setter is the standard molar enthalpy of space K at the temperature of interest. So that's why the definition of a standard reaction enthalpy is the sum of this product of this standard molar enthalpy and minus the sum of this the reactant of enthalpy of this system. Right, so for example, this is example. So standard enthalpy of a combustion. This is also similar things. The standard reaction enthalpy for the complete oxidation of an organic compound to the carbon dioxide gas and rich dihydrogen oxide. So this is the example. So they have this kind of combustion enthalpy. So actually, this is the all this kind of definition and also explanation also similar. So you can just think about that what kind of reaction is occur for the kind of chemical process. Okay, so yeah, so there is some kind of the tables which expressed about the standard enthalpy of formation and the combustion of organic compound at this 298 degrees Kelvin. So for benzene, they have formation enthalpy of 49, and this combustion is the 3,268. There's ethane, glucose, methane, methanol. So there could be, how can I say, some kind of the question about this, how the kind of a reaction occurs and then which enthalpy change can be come together for the kind of reaction. You can simply use this kind of a table. So actually there are, you can find this kind of table in the Google also. So you can simply use the tables. So actually the key things for this thermal chemistry is the Hess law. So Hess law is the standard enthalpies of individual reaction can be combined to obtain the enthalpy of another reaction. So what this means? So if there is some kind of A plus B equals C, then this standard enthalpy of this overall reaction is the sum of this each individual reaction. Yep. So this is law. The standard enthalpy of overall reaction is the sum of the standard enthalpy of the individual reactions into which a reaction may be divided. So the individual step need not be realized in practice actually. So you can simply reorganize the kind of a reaction in your performance, but you can only have this final forms and initial forms because this is state functions, right? Okay, so let's solve an example about this kind of Hess law. Actually, the Hess law also involved the kind of chemical reaction. We learned about this kind of enthalpy change and also this all these things. So if you can understand this Hess law, then you can all understand about this thermochemistry. Okay, so using Hess law, the standard reaction enthalpy for the hydrogenation of propane is the CH2, CH, CH3 gases state, and H2, and CH3, CH2, CH3. And this is the enthalpy change of minus 124 kilojoule per mole. And the standard reaction enthalpy for the combustion of propane is the CH3, CH2, CH3, this one, plus 5O2 equal going to 3 CO2 plus 4 H2O. And this is the minus 2022, 220 kilojoule per mole. So let's calculate this standard enthalpy of a combustion of propane. And standard enthalpy of formation of water is the minus 286 kilojoule per mole. So I will give you a few minutes for this calculation and let's calculate together. Okay, so let's solve together. So first, we have this kind of chemical reaction, which is the hydrogenation of propane, which is the hydrogenation. And this is enthalpy changes this value. And the combustion of propane is this reaction, and they have this kind of enthalpy change. And this enthalpy of formation of water is the minus 286 kilojoule, and this is the H2 gas plus O2 gas is the right. So we can simply say that this is the C3H6 gas for some kind of simplification, and plus H2 gas, and this is the C3H323A gases. Right? Then C3H8 gases plus 5O2 gases. And this is a 3CO2 gas plus 4H2O liquid. right? So then we have H2O liquid to H2 gases plus O2 gases. So this is the minus 124 kilojoule per mole, and this is the minus 220 kilojoule per mole, right? And this is the plus 206 kilojoule per mole, because this is the minus, and the reverse process will be plus, right? So then we have C3H6 gases plus 2 O2 gases, 3 CO2 gases plus 3 H2O, and right. So I just erase this kind of 1H2 and this 2 over 1 O2, and just reduce this 4 to this 3. This is just for kind of simplification of reaction to calculate easily using this kind of enthalpy changing. So by adding all this value, the enthalpy change of this value will be minus 2000 right? So actually, the key things of this system, how can I say, the you have to understand what is the combustion process, because there is the how can I say, so the key things is the making this kind of combustion reaction from this the given reaction. But for that, you have to understand what is the kind of combustion reaction, and then. But I don't want to fully understand about the things. If this kind of question is yeah. So this is just kind of for your information. So if this kind of question is occurred, is given in the midterm or final exam, then I will give this kind of final form of this solution, and then make you to derive this kind of three difference equation from this given the information. So such a thing you can do this, solve this as well. Okay, so anyway, the key things of this information is the all this reaction is the some of this individual reaction. So that's the key things point of this Hess law, and also the thermochemistry. Yeah, so like this. So I'll give you these things for you to solve this example here. And then you should divide this, uh, derive this kind of the individual equation from this system. So that things you have to, you can understand, you can do through this examples. Okay, so can I say this is also a similar concept. So standard enthalpies of a formation is the similar thing. So standard enthalpies of formation are defined in terms of the reference state of element. So the standard reaction enthalpy is the expressed as the difference of standard enthalpies of a formation of product and reactants. So this is also similar to this standard enthalpy of a reactant. So the sometimes computer modeling is used to estimate this standard enthalpy formation. Okay, so the standard enthalpy of formation means the standard enthalpy of formation of a substance is the standard reaction enthalpy for the formation of a compound from each element in their reference stage. So what is the specification of the reference state? The reference of element is the most stable state at the specified temperature at 1 bar. So what this means, for example, in terms of nitrogen is the nitrogen molecule, okay, so for N2 molecules, right? So the actually this is the also part of standard enthalpy of reaction, but the standard enthalpy of formation is the difference between this reference state to this compound state. Okay, so this is the concept. So in terms of ions in solution, the standard formation of enthalpy is zero. This is kind of a convention. In other words, rules. So this is kind of appointment of this peoples. Okay, so this is some example, the standard enthalpies of formation of inorganic compounds. So such as thing. They have this kind of enthalpy change. So this is also similar to the other concept of standard enthalpies. So the reaction in reaction enthalpy in terms of enthalpy of formation. So conceptually, we can regard a reaction as proceeding by decomposing the reactants into their elements and then forming those elements into the product. So for example, the how can I say, this kind of process is occurred from this reactant and forming this element, and this element is forming this product. So this kind of process is occurred, and we can have this kind of standard reaction, the enthalpy, by dividing, I mean, the extracting this value from this reaction value. So for example, there is a product enthalpy, standard formation enthalpies, and then reactant standard enthalpy formation. This is the V sigma F H theta, and this is a V F delta F H theta, and just minus this one to this is the standard reaction enthalpy, right? So the brief illustration or the standard enthalpy of the reaction can be written as like this. This is kind of example. So if we have two HN3 liquids and two NO gases, and we have H2O2 liquids and four N2 gases, and this can be calculated as the standard enthalpy formation of this one and this one, and standard enthalpy formation of this one and this one, and just the you can find that kind of value for this system in some kind of a data set, and then they have this kind of values, and just a sum of all these things, then we have this standard reaction enthalpy. So actually, this is the concept. So the all things what I have said in today's classes is actually almost the similar concept. So and also they all have the similar way to calculate. So you just require to understand the kind of the transition, the different types of transition and which types of transition occur in the things, and then how can we calculate the kind of standard formation temperature? And that's also really simple. We can just simply add all these things, and just the be cautious about this signal of which values. Okay, so I think we had better start this class here. And before start this class, I'll give you a quick summary in Korean. 네, 지금까지 연력학에서, 그러니까 열화학에 대해서 저희가 배운 거죠. 서머 케미스트리에 대해서 배운 거죠. 그러니까 이제 뭐 다 비슷한 컨셉이긴 한데 이제 화학 반응에 있어서, 그러니까 정말로 이제 물리화학이라는 수업이잖아요. 그래서 화학 반응에서 이러한 그 엔탈피 변화가 어떻게 지금 나타나는가 하는 것들에 대해서 여러분하고 지금 배워보고 있었습니다. 그래서 지금 네, 배웠었고, 이제 그 중에 이제 핵심적인 게 뭐 스탠다드 엔탈피 오브 트랜지션, 결국은 사실 뒤에 계속 쭉 나오는 게 이 얘기가 계속 나오는 거예요, 사실. 스탠다드 엔탈피, 이 얘기가 계속 나오는 거였습니다, 사실. 이게 뭐냐면 그 엔탈피의 변화, 그러니까 어떠한 그 시스템의 상태가 변할 때, 뭐 예를 들어 리퀴드에서 가스로 변한다던가, 아니면 가스에서 리퀴드로 변한다던가, 아니면 솔리드에서 리퀴드로 변한다던가, 그런 어떤 상태가 변할 때 나타나는 그 상태가 변할 때 나타나는 엔탈피의 변화를 나타내는 게 바로 엔탈피 체인지, 스탠더드 엔탈피 체인지인데, 특히나 그런 트랜지션이 발생할 때, 스탠더드 엔탈피 오브 트랜지션인데, 그런 트랜지션이 그 스탠다드 스테이트에서 발생한다고 할 때 이거를 스탠다드 엔탈피 오브 트랜지션이라고 합니다. 스탠다드라는 걸 뭐냐면 그 1기압이라는 원바라는 그냥 일정한 압력에서 그게 어떠한 뭐 아이온이라든가 어떤 다른 형태를 지지 않고 피어한 원래의 상태를 지니고 있을 때, 어떤 변화가 되지 않고 피어한 상태에 있을 때에 그 상태에서 어떠한 그 반응이 일어났을 경우에는 이런 스탠다드 엔탈피라고, 스탠다드 폼이라고 얘기를 하고 있는 거죠. 그래서 뭐 그거에 대한 다양한 예시로 뭐 리액션, 피지컬 체인지가 발생하는데 뭐 이렇게 이런 다양한 예시들이 있고요. 이런 다양한 예시들이 있는데 이런 예시들에 대해서 계속 설명을 하는 거죠. 근데 그 엔탈피 체인지가 뭐냐면 이 각각의 이 프로세스들을 모두 더한 거. 그러니까 스테이트, 이게 중요한 거는 결국 여기서는 엔탈피가 상태 함수라는 거, 스테이트 펑션이라는 것만 여러분이 기억을 하시면 돼요. 그래서 초기와 중간에 어떤 단계든지 간에 초기와 끝만 알면은 이 중간 단계의 것들은 관여하지 않는다, 고려하지 않는다는 거죠. 그래서 우리가 초기 상태와 끝 상태를 알면은 요거를 유추할 수도 있고, 요거를 알면은 최종 상태 유추할 수 있고, 요런 어떤 프로세스가 있으면 요거랑 요거를 알면은 요거를 또 유추할 수 있고, 이런 것들이 나타내 준 게 바로 횟수로우죠. 다 더한 거는 이것도 결국 횟수로우죠. 결국 모든 프로세스는 더한 거의 합식에 같다. 그 얘기를 계속 한 겁니다. 뭐 이것도 마찬가지고 이것도 결국 뭐 말이 좀 어려웠는데 사실은 이게 지금 이렇게 올라갔다가 이렇게 변화를 계속 하는 거죠. 반응. 이런 식으로 반응을 할 때 요 반응에서의 엔탈피 변화를 계산을 이런 식으로 다 더해서 한다. 이렇게. 그러니까 결국은 이게 지금 사실 컨셉은 굉장히 심플한데 여러분이 좀 어려워하는 거는 이런 화학 반응이 어떻게 지금 발생을 하는가를 잘 이해를 못하기 때문에 어려울 수가 있어요. 그래서 이제 그런 것들은 여기 이 시간에 하는 건 아니고요. 사실은 여러분 일반 화학이나 뭐 이런 데서 배웠을 내용들이기 때문에 어, 뭐 그런 내용을 저희가 다루진 않을 거고요. 여러분이 일단은 여기서 기억해야 될 거는 어떠한 반응이 있을 때 그러한 반응에 있어서 그 열의 출입을 우리가 이런 식으로 계산을 해줄 수가 있다. 이렇게만 이해를 하시면 될 것 같습니다. 그래서 이것도 마찬가지로 똑같은 얘기 하는 겁니다. 케미컬 체인지, 그러니까 리액션에서 나타나는 게 뭐 이런 식으로 나타낸다 하는 것만 이제 여러분이 아시면 되죠. 헬스로우도 같은 말이고요. 그래서 이거 문제 풀어봤는데 여기서 여러분에게 그때 중요했다고 뭐 여러분이 아셔야 될 거는 뭐 이게 뭐 리액션을 제가 만들어라 뭐 여러분이 구해라 막 그렇게까지는 안 할 거예요. 그래서 요렇게 주고 요 리액션이 이렇게 돼야 되는데 요 과정에서 그 이때에 그 이거를 구해라. 엔탈피 체인지를 구해라. 그럼 여러분이 요거를 바탕으로 요렇게 유출을 해서 유출항이 도출을 해서 요거를 이제 구할 수가 있어야 됩니다. 그런 것만 여러분이 하실 줄 알면 돼요. 굉장히 심플하죠. 반응까지 들어가면은 굉장히 어렵습니다. 포메이션도 마찬가지예요. 리액션을 통해서 뭔가 프로덕트가 생성될 때 필요한 엔탈피를 포메이션이라고 하는데 뭐 똑같은 얘기 하는 거예요, 사실. 네. 근데 뭐 다양한 타입에 대해서 얘기를 하는 거죠. 그러니까 리액션 타입이 조금씩 다른 거고 거기에 따라서 어떻게 우리가 계산하는가 결국 같은 얘기를 다 한 겁니다. 여러분이 뭐 크게 이해하시는데 어려움은 없었을 거라고 생각을 하고요. 네, 그럼 여기서 일단 수업을 마치도록 하겠습니다. 네, 여러분 수고 많으셨고요. Okay, so thank you for your attention and see you in the next classes.